Okay, we got to talk about a conservation of angular momentum. Okay, so quick little recap of before for linear movement momentum. Oh, this just came out of the box. Give it a few minutes. Don't laugh, Kate. It's a defective product. I'm gonna call them and berate some helpless customer service representative for something they had no fault in. Just yell at them. How dare you send me a faulty marker? What?
Someone told someone to put all the duds back in the box.
Hey, look.
Yeah.
Okay. So before we covered this idea. So momentum is mass times velocity. That is really useful for stuff like collisions. So it could be this block, call it mass 1 traveling at velocity 1, and it might hit into a block at mass 2 traveling at velocity 2. What you would do is you'd say, well, the total momentum of that system, m1 v1 plus m2 v2, is conserved. So, hello, good morning.
As well.
Certainly. So what conservation of momentum tells us is that if two things, collide, this quantity, whatever that number is, would stay the same, right? Same thing if you got, here's two astronauts in outer space, right? They push off each other, but their momentum is going to stay the same, right? The momentum of the system stays the same. That's not a good enough review. Thorough. Okay, so the same thing's true for angular momentum. Okay, so let's look at this first one. Bob the skier. He's practicing his double backflips, and so here's a person. Let me put his skis on, I guess. That's him. Okay. So let's think about this. So I guess just take my word for it. The angular momentum of a system is going to be conserved. Now that's actually a caveat to that. Maybe you guys can guess the caveat. It's very similar to this one. The caveat of this one is, well, that momentum is conserved unless someone comes in from outside the system and exerts an external force. Right? So if two blocks are about to collide and then I stick my hand in and I block one of the blocks, right? I push the blocks, or I stick a magnet here and I pull the blocks, well, that's going to change the momentum of the system, right? And in fact, we know the answer to this. It's that force multiplied by time would tell you the change in momentum for the system. So if you exerted 100 newtons for 5 seconds, you would change the momentum by 500 momentum units, right? Lindsay, did you get one of these? Good thing you're so sharp. It's all those Dragon Ball Z's I watched.
Exactly.
So anyway, so who can guess? What's the caveat for Bob's angular momentum is going to be conserved as he flies through the air, unless
he runs into a tree.
That would be one way, because that tree. So if Bob was spinning and he hit a tree, that tree would be exerting an external force, but we're talking about rotation, so we're going to say a torque. So if something's spinning, right, it's going to maintain that angular momentum unless you exert a torque on the system. Does that make sense? Yesterday we derived this. Hopefully this rings a bell. The torque times the time would tell you the change in the angular momentum. Yes, possibly.
Yes.
Please. Yes. Okay. Now Bob is spinning. Okay, he's doing a backflip. Okay, double backflip. Now, Bob right now, he's a bunch of mass. So Bob has a certain. Let's first write this. He has an angular momentum. What's the formula for angular momentum for a complicated object like a person? That's I. In the right ballpark. Momentum is mass times velocity. So angular momentum is what's the angular version of mass? I. What's the angular version of velocity? Omega. Make sure you know this formula. That's a really big one. If you were thinking this, is it R times P? That's the definition of angular momentum for a point mass. Okay, so that's if you have a single mass at a single radius. But if it's a more complicated object like a sphere, a cylinder, a bob, right? Then you have to. By the way, would it be easy to calculate Bob's I value? No. You'd have to somehow calculate. You'd have to figure out his center of mass, right? And then do some crazy calculation of all his MR squared values. Because remember, your I is the sum. Bob is made out of a lot of particles, so you'd have to do it. You can figure it out empirically, though. You could probably measure it. Okay, so when Bob does this, so let's say he goes from a state like this, trying to make him kind of tucked, this state, and in midair he goes into this state. What has he done?
He's increased or slowed down his rotations.
He would slow down his rotation. Well, why? That's what we're getting at. Why?
Like
Something to do with his center of mass.
Like air resistance.
We saw the little chair there. Air does not really come into play
The
there.
center of mass is spread out.
Radius, yeah.
That's closer. He's increasing his I value. Okay, remember your I value, guys. So remember for a point mass. For a point mass, your I value is mr squared. And if you're a complicated object, your I value is the sum of all your mr squared. Well, if you stretch your body out like this, aren't you increasing a lot of your R values?
Yeah.
I mean, you're made of a lot of point masses. You're made of billions and zillions of atoms, right? If you believe in that sort of thing, right? So when you do this, like you are increasing the R value on a whole bunch of your particles, right? Thus, you are increasing your I value. Does that make sense? Mm-hmm. So on the spinny chair, when I'm on the spinny chair and I'm doing this, right? Of course, my axis of rotation is this now, right? And I stretch my arms out. What am I doing to I? I increase the I value, right? So that now look at this formula. Which of these numbers has to stay the same? L. L is that big word. It's a big important word in physics. It is conserved. It means it stays the same. So angular momentum, L, is conserved. So if you increase the I value, the omega has to decrease. And conversely, if Bob wanted if he's doing his backflip and he perceives that I need to spin faster, he could then tuck again. The process can reverse. He could tuck, decrease his I value, and then increase his rotational speed. Okay? Is that a yeah? So you'll see that with figure skaters. They'll come in, kind of have their mass spread out, and then they start spinning, right? And then they'll tuck, right? You guys have seen this on TV, or maybe in person. They'll tuck, and then they'll stick their arms up sometimes to because their axis of rotation is vertical. So they stick their arms up, they're getting their arms right on that axis of rotation and really, really decreasing, making these R values as small as possible. So they can really, now you can think about the math here. If you could say you could divide your I by 5. So if you could get your I 5 times smaller by getting compressed, you'd multiply your rate by 5. Make sense? Now, I think with a figure skater, there's more complex things going on. The skates, they can actually get a torque to increase their speed with their skates because there's friction between the skates and the ice. That's the main principle is is this. So. Okay. With that, I mean, that's the main idea. There's not a whole lot else to cover. I mean, we can go over maybe a couple examples, but how to apply this. But that's the main idea right there is L equals I omega, unless there is, this is a big one too. This is his best friend right here. This is really big. So unless there is some net external torque on the system, then this is conserved. Okay. Does that make, are we sure that makes sense, this connection here? Yeah. Okay, so then how do you know if there's an external torque? Well, it's actually, most of the time it's just common sense. Like look at, like for Bob, you'd say, well, here's his system. Maybe imagine a little like ball, a ball around him and go, is there anything coming in from outside that ball that's like exerting a force or a torque on him? No. Maybe if you really want to consider air resistance, if you're like, move on to that. Oh, what about air resistance? So like, what might exert a torque? I don't know. Someone could throw a snowball at him, right? He's doing a backflip. Someone hits him with a snowball here, right? That would exert a force at a radius that could increase his angular momentum, right? Or if I hit him in the head, that would decrease his angular momentum because the torque opposes the momentum. Okay. All right. How are you doing, Julia?
I'm good.
It's Julia. That's what she is. Okay. All right. So number 7 is basically what I showed you here. Oh, I guess for the for the Twitch fans, there's just a rotating chair. If you sit on a rotating chair, you can do this with an office chair. If you spin around and then you tuck your arms in, you'll find yourself rotating faster. What? Hopefully, you're referring to a time when you were like a freshman.
Yeah.
You can use mine, Caleb, if you want.
Actually, every boring part, every boring spot that keeps up.
Anyway, Albert is sitting at the center of a rotating platform. He's spinning at 20 revolutions per minute. Let's look at the numbers here, because it might not be obvious what's going to happen to his. By the way, a little review for you. 20 revolutions per minute. What letter is that describing? F. It's a frequency. So Albert is sitting on this. So here's Albert. He's sitting on a rotating platform. Okay. He's rotating at 20 revolutions per minute. So by the way, suppose you were like, well, I know that we always write omega as, what do you call it? Radians per second. Radians per second, right? So how do we convert this to, how many radians per minute is this? How many radians are in each revolution? There's 2 pi. So this would be 40 pi revolutions per minute, which means it's.
Wait, it's radians per minute?
Oh. Did I say radians or revolutions?
Said that.
I said earlier, okay, I'm going to say radians. Okay, so that would be divide that by 60. You'd have 2/3 pi radians per second. Okay. Now here's the thing. Think ahead. That's the question is, could I maybe just focus my attention on this number instead? So we're going to get at that in a minute. Okay. So Bob or Albert is going to tuck his arms in. So when he tucks his arms in, okay, what did he do? What does this do when he tucks his arms in?
Spin faster.
He's going to spin faster. We know that intuitively. So if this was I, say this is I initial, his new I value is half as big. You understand? So if you look at this formula, L equals I omega, what happens if you cut this in half?
Double your omega.
it would double this number, and what that would do is that would conserve that number. Okay, if you cut this in half, you double this stays the same. So let's say, okay, well, this is my omega, right? So let's double that. Hopefully this makes sense what I'm trying to get at here. There's an idea here. Okay, now let's turn that into radians per minute. What would I multiply that by?
60.
By 60. So 4/3 times 60 would be 80. And then how many revolutions per minute is that? Okay. Big moral of the story, right? Is that did I really have to convert my rotations per minute, my RPMs, into radians per second in order to finish this? No, what I could have noticed is like, well, because omega is it's just a multiple of the RPMs, then if I'm doubling omega, I am likewise doubling my RPMs. Is this making sense?
Yes.
All right. Sweet. It's a new record. You guys are bored beyond comprehension. It's only been 16 and a half minutes. That's pretty good. Yeah. Yeah, I know. It felt like an eternity, didn't it?
Let's see if we can outdo ourselves.
Felt like there was no escape.
Maybe we
Okay,
can do
guys.
15 minutes in calculus.
Have some work time. We've covered enough that, you could answer, pretty much every question on here. Like, there's not much more for me to cover. Of course, we'll go over a couple more examples tomorrow, but, I don't know, use this time. You got 20 minutes to knock out a bunch of the assignment, okay?
When's our quiz?